So we're going to talk about pressure and the behavior of gases. We've talked a little bit about this before, but now we really want to give a definition to pressure. Pressure is the force on the walls of a container from when the particles bounce against it. So if you think about the room that you're in right now, it's full of gas, and all of those little gas particles are bouncing around and they're pushing on the walls, but it's not so strong that it's going to make your room explode or anything. And so what that would look like would be if you picture this box here and you know that gas particles are really spread out. And so I think, okay, I have all these little gas particles in there. And they're pretty spread out and they're bouncing around and they might hit the walls and they might hit you, but it's nothing too strong. It's what we call 1 atmosphere of pressure. It's a regular amount of pressure. But you know that when things get under high pressure, they have the capacity to explode. And so what that would look like is if I put a whole bunch of particles and I increased the amount of gas in that room with you, because there's so many more particles, they're going to be pushing on the walls a lot stronger, and they're going to be bouncing against it and pushing, and eventually when you get things under high enough pressure, the force of those particles can actually cause the container to burst. So those particles push on the walls with such a strong force that it could actually burst the container open or the room open or whatever container we're talking about. And so the reason that we care about pressure so much is we want to measure it very frequently, and it tells us many different things. So barometer is the tool that we use to measure atmospheric pressure. And so this would be something that would be done by the weatherman. And so usually when you look at the weather, all you really care about is the temperature. If you get a little bit more detailed, though, especially if you're going to be a meteorologist or a weatherman or woman, then you start looking at the atmospheric pressure. So yes, there's pressure over your head from the atmosphere, but there are slight variations in it, and that can tell you important things about the weather. So when there's a high pressure day out, it's fairly easy to have like a nice weather day. But when the pressure gets lower, then we're more likely to have bad weather. And so this thing right here is the barometer. And what happens is the pressure from the air pushes down on this liquid in the bottom. And the higher that pressure gets, it pushes that liquid up inside of this tube, and we can just measure whether it's a high or a low pressure day. And that's what the weathermen do. It helps give them a clue about, is it going to be nice weather for a few days or bad weather? They can kind of track what's going on with that pressure. Another place you hear about pressure is when you go to the doctor and they take your blood pressure. And so normal blood pressure, if you go to your doctor, is 120/80 mmHg. And so this is the unit that the doctors are measuring your blood pressure with. There are actually several different units for blood pressure, though, and you're going to see all 3 of them. So one possibility is atmospheres, because there's 1 atmosphere of pressure above your head. You also might have millimeters of mercury, which you can abbreviate mmHg. And this literally means, if I go back up to that barometer picture, how high up, how many millimeters high has that mercury moved in that tube? That's where mmHg comes from. The last possible unit you might see is kilopascals, kPa. But if I talk to you about these units, you don't really know like what's high and what's low for them. So to give you a reference, 1 atmosphere equals 760 millimeters of mercury, and that equals 101.3 kPa. And that gives you a frame of reference, where if I just said that my pressure is 200, you don't really know what that means. But if I said that my pressure is 200 atmospheres, that's really, really high because normal is 1. But if it's 200 mmHg, that's much lower than normal. Same thing if it's 101.3 compared to that 200 kPa, again, that's a higher pressure. And so these numbers just give you a bit of a frame of reference for, well, is that pressure high or low? Like, what does that number mean? And so now I'm just going to remind you a little bit about how gases behave and how those particles work. So you know that gases are very spread out, they move around a lot, they bounce off of things, but what we talk about are ideal gases. And they basically say that they have perfect behavior and it just makes our calculations easier. You know that nothing in life is perfect, but we talk about ideal gases because it just simplifies our math and it makes the concepts just a little bit easier for us to think about. And so even though this isn't real, we say that an ideal gas has 5 characteristics that you're going to need to remember. And there's a little acronym to help you. It says RISN. So we're going to talk about what each of those letters stands for. R means random. Those molecules move randomly. So when those gas particles bounce around, they're not following a pattern. Nobody's telling them where to go. They literally just bounce off the walls, bounce off each other, and kind of do whatever they want. The I stands for independent. The molecules don't attract or repel each other. They're not friends going down the hallway and bouncing around together. Those particles basically have nothing to do with each other. The S stands for straight. The molecules only move in straight lines, which means they're only going to move like this. You'd never follow the path of a particle and have it go like that. That's not going to happen. The E stands for they have what's called elastic collisions. Basically, that means when they collide and they hit each other or they hit the walls, they don't lose any energy. They just bounce and they move on with their day. They keep the amount of kinetic energy that they have and nothing gets lost. Lastly, the N is no space. Basically, those particles are so small that they don't really have any volume, they don't take up much space themselves compared to this giant container that they might be in.